Okay, let me introduce. The next speaker is Hans-Peter Deifel. Probably I pronounce it really, really wrong, but so please, Hans, whenever you want.
Yeah, thank you. That was perfect, actually, the pronunciation. So welcome to my talk. It's titled Coalgebra Encoding for Efficient Minimization. I'm Hans-Peter Deifel, and this is joint work with my good-looking co-workers Stefan Milius and Thorsten Wissmann, which you can see in the pictures. And now, as is evident from the title, this talk is concerned with minimization. And since there are a few different notions of minimization around, we need to clarify what we actually mean by minimization here. And specifically, we're talking about minimization of state-based systems, so systems consisting of different states and transitions between them, and in our instance, even a designated initial state. And minimization for these systems obviously means to reduce the number of states as much as possible while still preserving the overall system behavior. Now, there are quite a few algorithms that do this in the literature, like, for example, the Page-Taschen algorithm for partition systems, transition systems, and so on. Hopcroft's automata minimization algorithm, color refinement, which is an intermediate step in graph isomorphism checking, or things like Markov chain lumping and many more. And they all have a very similar structure to them, and also a very similar runtime, as you can see on the slide. Here, M stands for the number of transitions, and N is the number of states. And the goal of this project is to subsume all these algorithms under one umbrella, so to say. And to do this, we need to look at some of the similarities. And on a very high level, a similarity between them is that they consist of two steps. So those two steps would be reachability analysis and quotient computation. Here, reachability is just the obvious removal of unreachable states, like, for example, this polygon state that doesn't have an edge from the initial state and so is unreachable and doesn't contribute to the system behavior, so we can remove it. And the second step is the quotient computation, which means we need to identify equivalent states that behave the same in the system, and we can merge them in the resulting system. So for example, here, the two squares are both, they look the same and they have no outgoing transitions. And so in the resulting system, we can just remove them and merge them together to one state. And then we arrive at the minimal system. Now, for this, we want to provide an algorithm that does both of these steps, and we want it to be very general and treat very large amount of different systems. And we choose the framework of Coalgebra for this. So Coalgebra uses the language of category theory to provide a very general notion of state-based system. And in this talk, we specifically treat coalgebras in the category of sets and functions. So in this category, a coalgebra is defined as follows. It consists of a set of states and a successor map, which is also called a coalgebra structure. Now, this map takes a state from X and maps it into some kind of successor structure, which is determined by this type functor here. So this type functor is just an end functor on set, and it determines the types of transitions that the system can have. So for example, coalgebras for the power set over A times X functor, they correspond to labeled transition systems. Also, deterministic automata correspond to coalgebras for the functor 2 times X to the A, and Markov chains correspond to this real valued functor here. And the nice thing about coalgebras is that they come with a few very useful notions out of the box, like, for example, coalgebra homomorphisms, where a coalgebra homomorphism is just a function between the state sets of the coalgebras that preserves the coalgebra structure. And now this homomorphism induces a notion of equivalence, which is called behavioral equivalence. And it's defined like this: two states are behaviorally equivalent if they are identified by some coalgebra homomorphism. So this means if there exists a coalgebra homomorphism that maps those two states to the same state in the codomain, then the original states should be treated as behaviorally equivalent. And this corresponds to well-known and useful notions in the individual systems. So for label transition systems, we get standard strong bisimilarity out. For automata, we get language equivalence even. And for this real valued functor here, or coalgebras for this functor, we get a form of weighted bisimilarity. Now, if we identify as many states as possible, such that the resulting system doesn't contain any two behaviorally equivalent states, then this is what we call a simple quotient. It's the smallest quotient of the given coalgebra. And this means that we have now provided a coalgebraic notion for this quotient computation that I showed you on the previous slides. And the second step that we need to treat would be reachability analysis, which also has a correspondence in coalgebra, but we need to move to pointed coalgebras in this case. So a pointed coalgebra is just a coalgebra equipped with an additional point. So this I and j here, and this is just a designated initial state, and we model this as a function from the singleton set to the state set that just picks the one state. Now, homomorphisms for these pointed coalgebras need to additionally preserve the point, and an injective homomorphism represents a subcoalgebra. So we can do the same game that we did for quotients. The least subcoalgebra then is something very useful. It's called the reachable subcoalgebra, which doesn't contain any unreachable states. And this corresponds to the obvious notion of reachability in all the different systems. So for example, for label transition systems and automata, we get reachable states, while for these weighted systems, we need to be a bit more careful and get some form of weighted reachability, so that where we count 0 edges as having no edge. So we need to treat those differently. Now, having quotient computation and reachability on the coalgebraic level, we can combine those and just do them one after the other. So let's say we start with a pointed coalgebra C, and then first compute the reachable subcoalgebra, and then finally compute the simple quotient. Then it works in this case, as we have seen on the previous slide, like first removing the reachable states and then identifying equivalent states. But we want to treat other systems too, and for example, also weighted systems. And in this case, they can even have negative weights. So now in this system, no state is unreachable. We won't remove any if we do the reachability computation. But if we compute the quotient, what happens is that the transitions here are summed up in the resulting system. So we actually get this system. And as explained previously, a 0 edge means having no edge. So this would correspond to this system. And so the box here became unreachable in the resulting system. And so this is certainly not the minimal one. We have a state that doesn't contribute to the system behavior. And so the lesson is that we need to change the order. We need to do quotient computation first, and then only then remove unreachable states, because quotienting can produce new unreachable states. And this is now called the well-pointed modification of a given coalgebra. And the thing that's to note is that having this order is only necessary for functors that don't preserve inverse images. So if your functor does preserve inverse images, then you can use the more standard different order of first computing reachability and then quotienting. So now, as I said previously, we want to have an algorithm that computes the well-pointed modification for a given coalgebra. and we want it to be implementable in a computer. And so we need to have some way to talk about coalgebras in a very concrete sense, and we need to be able to store them in computers and files and stuff. And this is where we introduce so-called Coalgebra encodings. They are formed to encode abstract coalgebras in a very concrete way that allow computer treatment, and it's defined like this. So the encoding for a functor f consists of an abstract label type A. That's just for each functor something abstract, and the encoding map flap here that takes an abstract successor structure here from fx and produces a list of labeled successors. So you can think of these bags as lists of labeled successors. In reality, they are multi-sets, so sets with repetition allowed. And obviously, we want to encode different coalgebras differently to distinguish them. And so we need some form of injectivity condition, but we don't require the encoding map itself to be injective only when paired with this fbang value, because that retains some additional information. I'll show you in a second why. To do this, we need to look at a few examples. So coalgebras for the power set functor here, they correspond to unlabeled transition systems. And so this abstract label type is actually unnecessary, but we still need to provide it. And so we just use the singleton set as labels. And if we have a set of successors here, then our encoding map just pairs everything with the unit value, because in this case, we don't care about labels. And fbang, in this case, just sends everything to the star, which would distinguish between empty and non-empty sets, but that's not important in this case. But it gets very much more important for automata. So as I said, for automata, the functor is 2 times something to the a, and this 2 here represents finality of the state. So that's information about the state, not about the successes of the state. And let's say 0 means final and 1 means non-final. Then if we have a state that is final and has 1 A successor and 1 B successor, then our encoding map just returns the labeled successors as you would expect, but it drops the information about the finality of the state. And so we additionally need to keep this information via this fbang map here, which retains the finality, but drops information about successors. So that's why this fbang map is needed. And now this encoding is already very useful, and we have used it in a previous algorithm. Works like this: takes the encoding of a coalgebra, does a partition refinement step on it, and then outputs a partition on the state space such that behaviorally equivalent states are identified in the partition. And as mentioned, this is previous work. The features of this algorithm are that it's very generic. It works on a coalgebraic level and requires very little system-specific code. And it's also modular in the sense that the little bits of system-specific code that you need to provide are only needed for a select few basic system types, and then composed systems from those few types are automatically treated. So you don't need to provide the system-specific bits for every system out there, just for a select set of basic systems. And it's efficient in the sense that it matches the running time of many specific algorithms for specific systems, and in some cases even surpass the best algorithms at the time. So we now want to take it one step further and not just compute a partition on the state space, but also the structure of the coalgebra. And to do this, we need to look at how to compute the simple quotient first. So in particular, the transition structure of a simple quotient. And an algorithm for this would look like this. So it takes an encoded coalgebra and a partition on the state space and outputs the encoding of the simple quotient. But now for the first time, encoding appears in the output position of the algorithms, and our previous encodings are not yet suitable for that. So we need to apply some mild condition. To see why, let's look at an example. Here's an alternative encoding for the power set functor. So if you remember, we didn't need any labels for the power set functor, and so we set the label type just to the singleton set. But we can also distinguish between 2 labels and encode coalgebras for state sets of cardinality 2 differently than coalgebras for any other set and on any other set. And so this means that we just have two different ways of encoding coalgebras, and this would be perfectly fine in our previous definition of encoding. But it's a problem if we want to compute encodings, not just receive them as input, because we need to derive one encoding from another. And if we don't know what the target encoding will look like from the input encoding, then we cannot do this. So we need some additional condition on encodings, and we call this uniformity. So an encoding for a functor f is called uniform if this above diagram commutes for all x. It uses this filter function here, which is defined like follows. Filter for a set S, subset S of the state space, takes a list of successor states or labeled successor states and outputs just the labels to those states in S. And so what the above condition basically says is that identifying states other than X means that the labels are not changed that go to X. So this, if you trace the arrows here, it means that if we have an encoded coalgebra and look at the labels to X, then it should be the same as first identifying all the other states under the functor, then encoding the result and still looking at the labels to X. So labels don't change by identifying unrelated states. And this is a slightly technical condition, admittedly, but it still fits very nicely between two standard notions, namely naturality and subnaturality. So here, naturality just means that the encoding map itself is a natural transformation, and subnaturality means that for injective functions, this naturality diagram commutes. And also the inverse implications don't hold in general. So having this, we have constrained our encodings quite nicely, but we still need some additional functor-specific bits, which we call a minimization interface. So for each functor, we need a function called merge, which takes a list of labels and outputs a list of labels. And it needs to fulfill this condition here, which basically says that if we look at labels to a set of state S and merge those, we should get the same as first identifying all states in S and looking at the labels of the resulting state. So to see an example how this works, let's suppose we have a state called X, which has 3 successors with different weights. And our previous coalgebraic partition refinement algorithm determined that those 3 states should be the same. So they are equivalent. And then merge's job is to compute the new transition structure for these states. So in this case, for this weighted system, it would have to sum up the different weights on the edges. Now, for different systems, it works differently. For example, for partition systems, merge doesn't do much because we don't have any labels. It just needs to distinguish between empty success structures and non-empty ones. For weighted systems, as we have seen, it sums up the labels, as you can see here, and it also needs to take care of empty successor structures. And for automata, merges even the identity, because if you think about what happens if you merge states in an automata, you don't change the input symbols, you keep them in the resulting system. And so merge is just the identity here. And now we can use this merge in a construction to compute the quotient encoding. So this would look like this. If we start with an encoded coalgebra on the above and are given this Q here, and this Q is a surjective coalgebra homomorphism, which represents a partition that was previously computed on the state space. So what we want is we want to have this fx value, apply Q under it, so to identify all states that we want, and then encode the result. But we can't do that because we don't have this fx value to begin with. We only have the encoding of this fx value. And so we need to go this roundabout way of first applying this Q under the bag and then grouping by state, merging the respective transitions and ungrouping again. But the commutativity of this diagram says that it actually works and we get something out which computes the encoding of the simple quotient. And we can now plug this into the algorithm, which means that we have an encoding. We start with an input encoded coalgebra, apply the partition refinement step, and get out a partition on the state space, and then input this partition into our quotient encoding construction that you saw on the last slide, and additionally to the input encoding, and get out the encoding of the quotient. Now this solves the first step in our minimization procedure, but we still need to treat reachability. And reachability is for coalgebras in set is actually quite simple, because in set, reachability analysis on coalgebras just corresponds to a standard graph search on the canonical graph. So the canonical graph is just a standard graph without edge labels and directed edges. And this graph search means you just do a breadth first search or a depth first search on it to compute the reachable part of the coalgebra. And that's a very nice result. It relies on this definition of canonical graph that uses this tau function. This tau function needs to be provided for each functor and each state set x. And it goes from fx to the power set over x. And it takes this successor structure and basically returns all states that you cannot write t without. So that's a bit of a roundabout definition, but it's still equivalent to the original definition of canonical graph, which is due to Hans-Peter Gumm. And now if we precompose the coalgebra to this tau function, we get the canonical graph of a coalgebra. And in the examples, this looks like this. So the tau function applied to successor structure for automata just disregards all the input symbols and just outputs the successor states. Tau function for power set, where coalgebras correspond to unlabeled transition systems, doesn't need to do anything because we don't have labels, so we don't need to drop any labels. And the nice thing is that we can also provide this tau function for the back functor itself, where we are mainly interested in this back functor for encoding coalgebras. So it's not about the coalgebra for this functor itself, but it is about encoding of coalgebras for different functors. And we can also provide tau for this functor, and it again just drops all the labels. And additionally, since we have multisets here, disregards the multiplicity of the elements. Now, having tau for this back functor and for all other interesting functors, we can prove the following theorem. For an intersection preserving functor f with subnatural encoding flat. So remember that subnatural encoding is already fulfilled if we have uniform encoding, which we require. Then the canonical graph of a coalgebra coincides with the canonical graph of the encoded coalgebra. So we have the coalgebra and its canonical graph should be the same as taking the coalgebra, or is the same, and taking the coalgebra, applying the encoding function, and then the canonical graph of that. And now, since we know that they are the same, we can just do a standard graph search on the canonical graph of the encoded coalgebra to get the reachable part of the original coalgebra. And this is a very nice result. Still needed to prove it, but now the algorithmics are quite simple. And we can use this now to plug it into our coalgebraic algorithm that works now like this. We take our encoded coalgebra, compute the partition refinement on it, and output a partition, which we use to compute the quotient encoding. And this encoding is then used by our reachability step to finally compute the well-pointed modification of the given pointed input coalgebra. Now, this algorithm, it's still generic in the sense that it works on the coalgebraic level and only needs this additional merge function for each functor, but it's also modular in the sense that merge can automatically be derived for composite systems. So we only need to provide it for a select set of basic systems. And then it's also efficient in the sense that it's not less efficient than the original algorithm, because this quotient computation and computing the reachable part can be implemented in linear time in the input, and so it doesn't contribute to the asymptotic system and the asymptotic runtime of the algorithm overall. And there you have it, an efficient and generic algorithm that computes the well-pointed modification, just what we started out to do. This concludes my talk, and thank you for your attention. I'm happy to take your questions.
Thank you. Okay, you can send your reactions to Upload. If somebody have any question, you can raise your hand or ask the question in the chat as you wish. So to raise your hand, you have the reactions at the bottom, and you can click on raise your hand. In any case, Rafael sent a direct link. So during the break, you can join that room to continue discussing this presentation. So there's no question from the audience. Don't be shy. Okay. Okay, if there are no questions, then we thank the speaker again, and you can continue during the break, please, on this room. So thank you, Hans, and we will wait 4 minutes